Hello everyone, welcome to this 21st lecture session of the course Engineering Thermodynamics. In our previous lecture, we have started discussion on Carnot cycle. So initially, first we talked about different causes of irreversibility, and then in order to address our question which we have posed initially, that what is the maximum efficiency of a cycle. In order to answer that one, actually we have come up with the idea of a cycle which we call as nothing but completely reversible cycle. Okay, and that cycle is initially proposed by Nicholas Carnot, so that's why it is also famously known as Carnot cycle. Okay, so while we were discussing about Carnot cycle, I already mentioned to you all that there are different ways by which heat can be converted into work. Okay, but obviously the only consideration we are having in case of Carnot cycle is that we are having all the processes as nothing but reversible. Okay, so I told you that I'll be discussing about two approaches in this particular context. So already approach one I have established. So in case of approach one, what we are having basically, we are having our working fluid in the two-phase region. Okay, so here we are having our working medium that is in two-phase region, and apart from that, this cycle is actually obtained by combining different steady flow devices. Okay, and if I go to the pressure volume diagram of this particular cycle, we have already seen this is nothing but my liquid vapor dome. So this will be my first process 1 to 2, which will be inside boiler. That will be nothing but constant temperature heat addition. So during this process we will be having some QH amount of heat addition. Then I'll be having process number 2 to 3, that is nothing but inside the turbine. So we will be getting some WT amount of work over here, and this is my state number 3. Then I'll be having heat rejection process. Okay, and this heat rejection will be once again at constant temperature, and this heat rejection we will be doing in such a fashion so that we are reaching a state from which, when we are considering the reversible adiabatic compression inside the pump, we are once again reaching to our initial state. Okay, so in this particular process we have to supply certain amount of work that we call as nothing but our pump work. Okay, so this particular diagram we have seen in our previous lecture also. Now the unique characteristics of this particular cycle is that it is having all the processes as nothing but reversible. Okay, because all the processes are reversible in nature, so what I can do, I can just reverse all these processes. So it means that instead of coming from 3 to 4, I may go from 4 to 3 also. Okay, I may go from 3 to 2, I can reverse from 2 to 1, and I can reverse even from 1 to 4. So while I will be doing so, what will be happening? All my heat and work interactions direction will be reversing, and at the same point of time, the flow of the working fluid will also be changing. Okay, so it means that while I'll be reversing the process, instead of rejecting the QL amount of heat, we have to add over here QL amount of heat. Similarly, instead of obtaining some work, because we are now compressing during 3 to 2 process, so we have to add some work input. So obviously we will be calling that work input as nothing but compressor work. Okay, then here we will be having our condenser where we will be now rejecting QH amount of heat, and here we will be getting WT amount of work because we will be having some turbine which will be doing this particular process. Okay, so now the unique characteristics which I would like to highlight over here for these processes. So if I say the process number 1 to 2, so process number 1 to 2 is nothing but a reversible isothermal process. Okay, so 1 to 2 is nothing but an reversible isothermal process, because this process is happening at constant temperature and we are maintaining the temperature of the working medium equal to that of the temperature of the thermal reservoir. Okay, so we are not having any temperature difference. So we are having complete reversibility during this heat transfer process. Okay, so that's why I'm calling this 1 to 2 process as reversible isothermal. Now, obviously, whenever it is taking place in forward direction, we will be calling it as heat addition process. And while we are taking it in the reverse direction, we will be calling it as heat rejection process. Okay, then we have process number 2 to 3. So process number 2 to 3 is nothing but our reversible. Okay, and we already know that the process inside the turbine we consider as nothing but adiabatic. So this is our reversible adiabatic process which is happening inside the turbine. Then we have process number 3 to 4. So process number 3 to 4 is nothing but once again reversible isothermal. Okay, so 3 to 4 process is once again our reversible isothermal process. Okay, and then process number 4 to 1 is once again a reversible process which is happening inside the pump, and if we take pump as nothing but completely reverse operation to that of the turbine, then this process will also be adiabatic. Okay, so now when we are having this cycle operating in the forward direction, it means when heat is being converted into work, during that time we call this cycle simply as nothing but Carnot cycle. Okay, and when we are reversing our cycle, it means we are transferring the heat QL, amount of heat, from high temperature to low temperature QH, and while we are doing so, if we are supplying some W amount of work, it means we are nothing but reversing this cycle. Okay, so during the reversal, this particular cycle is known as reverse Carnot refrigeration cycle. Okay, so this is one very important point, that in the forward direction, because within this Carnot cycle each and every process is nothing but reversible, so because of that I can reverse back the process, each and every process I can move it in the reverse direction, and finally I'll be finding that while I am reversing the different processes, during that time we are having transfer of heat from low temperature to high temperature thermal reservoir, and we are adding certain W amount of work in order to achieve this. Okay, so during that time we call this cycle as nothing but reversible Carnot, and as the process is refrigeration, so we call this as reversible Carnot refrigeration cycle. Okay, so this is like all about using the approach 1, where we are operating our working medium in nothing but two-phase design. Okay, so now let me discuss about the another approach. So now we will be taking approach 2 for describing the principle of Carnot cycle, and in this approach 2 what I'll be taking, I'll take a cylinder piston arrangement. Okay, so here I will take nothing but one cylinder piston arrangement, and with the help of this cylinder piston arrangement we will try to see how we can achieve Carnot cycle, and this particular type of system will be nothing but a closed system. Okay, so obviously this will be our closed system because our medium is confined in between the cylinder and piston boundary, and at the same point of time over here we will be considering that our working medium is nothing but a gas. Okay, so here we will try to consider that our working medium is gas and it is in the single phase design. It means during the entire processes of the cycle we are having gas, always our working medium in the gaseous phase, so that's why we are having nothing but single phase working medium. Okay, so let me now start the process. So what I'll be taking, initially I'll be taking one cylinder. Okay, and say this is my piston, and inside this cylinder say I have some gas, and I have kept number of small weights over this piston. Okay, so this is my initial configuration of the piston cylinder arrangement. So that's why I'll be designating this particular point as nothing but my state 1. Okay, after this what I will do, now the same piston cylinder arrangement what I will be doing. So when it was at point number 1, corresponding to that, we were having nothing but this wall of the cylinder was adiabatic. So this was one adiabatic wall over here. Now what I'll be doing, I'll be contacting this bottom face of the cylinder with a thermal reservoir which is having temperature TH. Okay, and now during this time we will make the contact in between the source and this particular wall. So we will be finding that we will be having some transfer of heat, and let us consider that QH is the amount of heat which is transferring to my gaseous medium. Okay, so obviously what will be happening while we will be heating our so let me consider this was my initial position of the piston. So now what I am saying that while we will be heating the gaseous medium, upon addition of some energy from the source, we will be finding that the temperature within the gaseous medium will start increasing. Okay, but the characteristics of our Carnot cycle is that we have to operate this heat addition process in a reversible manner. Okay, so as we have to go in a reversible manner, so that's why what will be happening while we are adding the heat, during that time we will also shift the piston slightly in upward direction. How we will be shifting the piston in upward direction? We will try to remove some of the weights. So for example, now you can see I have given over here something around 7 weights. So corresponding to this second situation, the number of weights will be actually less. Okay, so I have removed some of the weights. So what I am doing, I am adding heat also, and at the same point of time, while I am adding heat, slowly I am removing the weights also. Okay, why I am removing the weights? Because this heat addition will try to, if I don't increase the, if I don't remove the weights, in that case, what will be happening? Our pressure within the system will remain almost constant, which is supplied because of the weights. So my temperature of the gaseous medium will start increasing upon addition of the heat. But what we want to do, we want to maintain this heat addition process at constant temperature. So that's why slowly I will remove the weights also, so that the rate at which we are adding the heat, expansion of the piston is also happening at the same rate. Okay, so in that case, what will be happening? Within the gaseous medium, we will be having nothing but our constant temperature condition. Okay, so it means that this is my heat addition process, and this heat addition process we are achieving in such a fashion so that the temperature should remain constant. So I can call this heat addition process as nothing but by reversible isothermal heat addition. So this is nothing but reversible isothermal heat addition process we are doing. Okay, so we will be finding that at the end of the heat transfer process, say this process has taken place, and at the end of the heat transfer process, I have my piston located somewhere over here, and say I have something around now say 4 weights on the piston. And now what I'll be doing, obviously I'll be removing now source once the heat transfer process has completed, and once again I will make my boundary of this medium as adiabatic. This cylinder boundary I am making as once again adiabatic. Okay, so this is nothing but my thermodynamic state number 2. So this is my state 2. Now after this, what I will be doing, I will keep the boundary adiabatic only. After this, I am keeping the boundary adiabatic only, and I will remove one by one all the weights. Okay, so now I will remove one by one all the weights. So while I am removing the weights, actually our piston will be further moving in the upward direction. So finally I will be removing all the weights. Okay, and while I was removing these weights, during that time what has happened, our boundary is once again adiabatic, and the thermodynamic state of the system the thermodynamic state of the system will obviously be state number 3. It will be changing the state because now we have removed the weights. So while we remove the weights, during the time piston has actually further in outward direction. Okay, so it means during this further expansion of the piston, particularly from here to here, during this particular expansion actually my boundary of the cylinder was adiabatic. So that's why this will be nothing but a reversible adiabatic process. Why reversible? Because we are having infinite number of small weights. So one by one we are removing the weight. So that's why process will be reversible. And boundary of the cylinder we are considering as adiabatic. So this process is nothing but my reversible adiabatic process. So this is in between the thermodynamic state 2 to thermodynamic state 3. So okay, so in between thermodynamic state 2 and 3, my process is nothing but reversible adiabatic. Okay, then now what I have to do, I have to once again complete the cycle. Okay, so once the piston is in the outermost position, after that I have to bring it back to the original position. Okay, so now what I'll be doing, I'll be contacting this particular cylinder periphery with one low temperature sink. Okay, so now here what we will be having transfer of heat from the gaseous medium to this sink, and say amount of heat which has transferred is QL. So while we are doing this heat transfer process, obviously the temperature, so this was my say initial position of the piston. Now while we are transferring out the heat from the gaseous medium, obviously its temperature will start decreasing if we are not changing its volume. Okay, so what we have to do now, one by one we have to add the weights, so that the rate at which heat is transferring, our piston is also moving in the inward direction at the same rate. Okay, so by doing so, what we will be doing, we will be able to maintain the constant temperature during the heat addition process. So this is nothing but my, because piston I am moving slowly and temperature within the medium is remaining constant. So that's why I'll be calling this process as reversible isothermal heat rejection. So this is my reversible isothermal heat rejection process. Okay, and at the end of this process, I'll be finding that my thermodynamic state of the system. So once again, what I will do, I will make this boundary as adiabatic. Okay, so I am making this boundary as adiabatic, and while I am making this boundary as adiabatic, at that time, say my piston is somewhere over here, and I have number of weights now on my piston. Okay, so I have number of weights on the piston. Okay, so this is my new thermodynamic state, which I am calling as state number 4. After this one, what I will do now I will keep the boundary as adiabatic only. So boundary will be once again adiabatic, and we will keep on adding the weights unless or until piston is reaching to the initial position. Okay, so once again I'll be having nothing but number of weights which were there earlier. So now the piston has reached to the initial state. So during this 4-to-1 transformation, our process is nothing but reversible adiabatic, and now this will be my thermodynamic state number 1, because I have to operate in a cyclic manner. So finally I have to reach once again to the initial point. Okay, so now if I plot this particular cycle on my say PV diagram, so what will be happening? For whatever the working medium we are having, that is actually in the gaseous phase. So this is my PV axis. So obviously that will be having some liquid vapor dome, but our entire medium is in the gaseous phase. So that's why we will not be operating in the two-phase region. Rather, we will be operating on the right of the two-phase region. Okay, so all the operations will be there on the right hand side of the two-phase region. So this was our state number 1. Say this is our state number 1. So 1 to 2 process, volume has increased. Okay, and during that 1 to 2 process, pressure will decrease slightly. So this is one important point I would like to highlight over here. So while you were talking about the previous process in this mode, So because we were operating in the two-phase regime, so that's why during this 1 to 2 and 3 to 4 process, though our main idea was to maintain the temperature constant, but pressure was also becoming automatically constant. Okay. However, while we will be operating the thermodynamic cycle in a closed system by using this cylinder and a piston arrangement, during that time you can see that during the process 1 to 2, we are removing some of the weights from the piston. As we are removing some of the weights from the piston, so because of that, what will be happening? We will be having decrease of pressure within the working medium while we are maintaining the temperature constant. Okay. So it means 1 to 2, while I will be going to point number 2, I will be having increase of volume and decrease of pressure, and at the same point of time, this line whatever I will be drawing, that will be nothing but a constant temperature process. Okay. So this is say my state number 2. Then from state number 2 to 3, what I was having nothing but reversible adiabatic expansion. So because of that, I'll be having adiabatic process 2 to 3. Then I'm having nothing but heat rejection process. So this is my heat rejection process, and during the heat rejection, we are adding some weights also. So there is some decrease in volume and increase of pressure. Okay, and finally we have nothing but our reversible adiabatic compression process inside the pump. Now one important point. So during this time we are adding QH amount of heat, and at the same point of time our piston is also actually expanding. So as the piston is expanding, it will do certain amount of work also. Okay, and obviously that will be during this time nothing but work done by the system. So the work which is done by the system over here, that I am writing as W1 to 2. Okay, and obviously you can easily determine the magnitude of this work because this is an isothermal process. So whatever the formulation of work I have told you for isothermal process, that will be applicable from 1 to 2 process. Okay, and during the process number 2 to 3, we are having nothing but heat transfer equal to 0. So there is no heat transfer, process is adiabatic, and we are having only the work which we are obtaining during this time. So this is also the work done by the system W2 to 3, and this we can obtain by using formulation of work done for an adiabatic process. Okay, then we have this process number 3 to 4. So during the process number 3 to 4, we are removing QL amount of heat from our working medium. At the same point of time, while we are removing the heat, we are adding some weights on the piston, which is actually compressing our volume. Okay, so because of that, we will be having some work done on the system. So amount of work done on the system, say I am calling as W3 to 4. Okay, so this once again you can calculate using the formulation of isothermal process. Then during this reversible adiabatic pumping process, our heat transfer will be equal to 0 and work will be done on the system. So work is done from 4 to 1. So that work will be obviously obtained using the formulation of adiabatic process. Okay, so this is my Carnot cycle using approach 2, where we have taken a gaseous medium inside the piston cylinder arrangement and we are operating our cycle in a closed system. Okay, so apart from this, there are number of ways for obtaining the Carnot cycle, but these are two important ways which I have actually discussed in this particular lecture. Now, based on the Carnot cycle, we are having two very important propositions. So, Carnot cycle propose two very important propositions. So the very first proposition says that it is impossible to construct a cycle that will operate at higher efficiency then reversible cycle operating between same thermal reservoirs. or I can say operating between same temperature limits. So this is the first proposition, which is derived based on the Carnot cycle. So it is impossible to construct a thermodynamic cyclic device that will operate at higher efficiency than the efficiency of a reversible cycle, which is operating between the same set of thermal reservoirs or same temperature limits. Okay, so if schematically I explain you, let me consider that I have a heat source at temperature TH and I have some heat sink at temperature TL. Now let me consider that I have one reversible heat engine. So RHE I am saying is my reversible heat engine, which is taking say QH amount of heat, rejecting QL amount of heat, and say doing some WR amount of reversible work. And at the same point of time, I have one more heat engine and say it is irreversible heat engine, IRHE. So irreversible heat engine. And it is once again say taking some QH amount of heat and say rejecting QL dash amount of heat and doing work as WIR. So this is the amount of work it is doing. Okay. So obviously you can see both these heat engines, reversible as well as the irreversible, are operating within the same temperature limits, within the same thermal reservoirs. So from this proposition 1, we are saying that it is impossible to construct a device which is having higher efficiency than the one which is operating in an irreversible manner. So it means what I want to say over here, that the efficiency of irreversible cycle will be always less in comparison to efficiency of the reversible cycle. Okay, so how we can prove this proposition? So let me try to show over here. So what we will be doing over here, let me consider that this is my TH and over here I have TL, and this is my first reversible heat engine cycle, which is say taking QH amount of heat, rejecting QL amount of heat, and doing say WR amount of work. Now if I say consider one more cycle, and that is my irreversible heat engine cycle, and this irreversible heat engine cycle is also once again taking QH amount of heat, and it is say rejecting QL dash amount of heat, and say it is doing how much work? WIR amount of work. Okay. Now if I consider the opposite proposition to that of the Carnot proposition. Okay. So if I say that while I am operating this irreversible cycle, say it is giving me higher efficiency in comparison to that of the efficiency of the corresponding reversible cycle, which is operating between the same temperature limits. Okay, so what I am saying, that my efficiency of irreversible is more in comparison to the efficiency of the reversible. Now you can see over here that I am taking the same heat input to both my cycles. Okay, so because of that, what will be happening? Obviously, if the efficiency of irreversible is more, it means I can clearly say that work done by the irreversible cycle is more in comparison to that of the work done by the reversible cycle. Okay, why? Because while I am supplying the amount of heat to both the cycles, that amount of heat is actually same. So QH amount of heat we are adding to both the reversible as well as the irreversible cycle. So because of that, what will be happening? If I am saying that efficiency of irreversible is more than reversible, then obviously amount of work done by the irreversible cycle will be more.
One of the viewers here is actually this video. He told us. All of it is an actual avid viewer.
Okay, so now what I have to do? Now what I have to do? I can write over here from my first law of thermodynamics. I can write that irreversible work will be nothing but equal to QH minus QL dash. So that will be greater in comparison to the reversible work. So reversible work will be equal to QH minus QL. So this QH minus QL and QH minus QL dash is nothing but I am writing from the law of the thermodynamics. So this is something which I can simply write from first law of thermodynamics or conservation of energy. Okay. So now if I write over here that if I combine both these systems, so from the combined system, if I say that I am getting some W net of work. So W net amount of work from the combined system, if I write it as nothing but equal to, so now what I have this cycle, first heat engine cycle is nothing but an reversible cycle. So instead of operating it in the forward direction, I can operate it in the reverse direction also. Okay, so this is one important point now I am doing over here. Initially, I have considered that my cycle, whatever I am having, one is irreversible, one is reversible. Okay, so while both are operating in the heat engine mode, obviously this irreversible cycle will have more efficiency than reversible, and this kind of condition will be applicable. Now what I am saying that in order to just have the reversible cycle, what I can do, instead of operating it in the forward path, I can operate this particular cycle in reverse path also. Okay, so if I operate this cycle in reverse path, what will be happening? QL will be my amount which I am transferring from low temperature thermal reservoir, and instead of now producing WR amount of work, it will be requiring WR amount of input work. Okay, and rather than moving down the heat, what will be happening? It will be rejecting now QH amount of heat to the high temperature thermal reservoir. Okay, so let me draw now this new system in my next slide. So this is TH, this is TL, and what I am doing, I am saying that my reversible cycle is now operating in reversible manner. So this is operating in the opposite direction. Okay, so because of that, what I am doing, I am transferring QL amount of heat and I am rejecting QH amount of heat over there, and while it is doing so, it is requiring WR amount of work input. Okay, so what I will be now doing, parallel to this, I am operating one irreversible heat engine cycle. So parallel to this, I am operating an irreversible heat engine cycle which is taking QH amount of heat and it is transferring QL dash amount of heat, and it is doing some work which is nothing but equal to WIR. Okay, so obviously as I have already explained you that WIR is more in comparison to that of WR. So because of this, what will be happening, whatever the W net amount of work I will be getting, that W net amount of work will be nothing but WIR minus WR. Okay, so this is one very, very important point. WR is the amount of work which is taken by this reversible heat engine. So that also we are supplying from the irreversible cycles work only. So because of that, net amount of work produced by this entire system will be WIR minus WR. Okay, so W net will be nothing but equal to WIR. We have already seen QH minus QL dash, and minus of WR we have seen as nothing but QH minus QL.
Sir,
okay,
can you explain it again why you subtracted them?
Okay, so what we are doing over here, this is now my reversible cycle is actually operating in the reverse manner. Okay, so if it is operating in the reverse manner, it means it is now acting like an refrigeration cycle. Okay, so if it is acting as a refrigeration cycle, it will be requiring some amount of work in order to transfer this QL amount of heat from low temperature thermal reservoir to high temperature thermal reservoir. Okay, so it means WR amount of input work is required for this refrigerator. Now parallel to this, we are having one irreversible heat engine which is producing WIR amount of work. Okay, so what we are doing, obviously we know that WIR is more in comparison to WR as per our initial assumption. So because of that, we will be saying that from this WIR, we are supplying WR amount of work to the heat engine. So whatever the overall output I will be getting from this system, that I am calling as W net. Okay, so from WIR, WR amount I am adding to the refrigeration. So obviously the net output I will be getting as nothing but WIR minus WR. Okay. And from our first law of thermodynamics, we already know that WIR is QH minus QL dash and WR is equal to QH minus QL. So from here we will be finding that W net is nothing but equal to QL minus QL dash. So it clearly means that my QL dash is less in comparison to QL. Then only I'll be getting some net work output. Okay. So now if you see this particular high temperature thermal reservoir, in this particular high temperature thermal reservoir, what we are doing, we are taking some QH amount of heat from it, and we are also rejecting some QH amount of heat to the high temperature thermal reservoir. So it means if I see in terms of the net amount of heat transfer for this particular thermal reservoir is equal to 0. Whereas if I talk about this particular second heat sink, so here we are having some net amount of heat transfer. Okay. So what I can do, I can remove this particular top thermal reservoir and directly I can couple this QH heat from this refrigerator to my heat engine device. Okay. So if I do so, what I will be finding that my system will be something like this. So this will be my system. Okay. And now in this system, you can see that this particular system is only exchanging the heat with single thermal reservoir TL, and it is producing some net amount of work. Okay. Because this TH thermal reservoir I can remove from the system. Why? Because here I am getting QH amount of heat and here I require QH amount of heat. So directly I can transfer this heat from refrigerator to the heat engine. Okay. So if I do so, what I am doing, I am finding a cycle which is giving me net amount of work done, and at the same point of time it is only exchanging the heat with a single thermal reservoir. Okay. So this is nothing but violation of which statement? This is violation of Kelvin-Planck statement of second law of thermodynamics. If it is violation of second statement of Kelvin-Planck statement of second law of thermodynamics, it means that efficiency of irreversible cycle cannot be greater than efficiency of reversible cycle. So this statement is actually not possible. Okay. So as this is violating this particular system for which we have considered that efficiency of our irreversible cycle is more than the efficiency of reversible cycle. For this particular cycle, we are finding that we are having a complete system which violates the Kelvin-Planck statement of second law of thermodynamics. So that's why this particular thing is not possible. Okay. So as it is not possible, so always we will be finding that efficiency of reversible cycle will be more in comparison to that of the efficiency of the irreversible cycle. Okay.
Sir, can you explain the last point again?
So what
where we are giving
okay. So
violation of Kelvin-Planck statement.
Yes. So why it is violating Kelvin-Planck statement? Because now this high temperature source I have removed from my system. Okay. So I have removed this high temperature source. So because of this, now whatever the system I have shown within the dashed line, in that system you can see that we are only exchanging the heat with low temperature thermal reservoir, and that is also producing some net amount of work output. Okay. And from our Kelvin-Planck statement, it is impossible to have a device which will operate in reversible manner and exchange heat with single thermal reservoir and produce some net amount of work output. Okay. So this is violation. So that's why efficiency of irreversible cycle cannot be more than efficiency of reversible cycle. Now let me talk about the second proposition of Carnot cycle. So second proposition says that all cycles operating in reversible manner between same temperature limits will have same efficiency. So this is the second proposition of the Carnot cycle. So for example, if I say I have some high temperature reservoir, I have some low temperature reservoir, and in between these, say I have number of cycles R1, R2, R3, something like that, and all the cycles are operating in reversible manner. Okay, so while all are operating in reversible manner, all will be having efficiency. So eta R1, say this is eta R2, eta R3, eta R4. So all the cycles will be having same efficiency. Eta R1 will be equal to R2, will be equal to R3, and eta R4. So what I mean to say over here, while we are operating a cycle between the two temperature limits, we can operate the cycle by different ways. Okay, so one of the way I have shown you by using the two-phase regime working fluid in such a fashion, so that we are operating in the two-phase regime and we are combining different steady flow devices. Another approach I have shown you where we are having working fluid in the gaseous medium only and we are operating in the closed medium. Okay, so like that we may have number of mechanical arrangement for obtaining or for operating the heat engine in a reversible manner. But if all the different kind of heat engines all are reversible, but their mechanical arrangement may be different. Okay, but if all are operating within the same temperature limits, all will be having same efficiency. Okay, so efficiency of all the cycles operating between same temperature limits, if they are operating in the reversible manner, that will be same. Okay, so this is one very important point which also you should know. Now let me go to our next very important topic, which we call as nothing but absolute thermodynamic temperature scale. So now I would like to first quickly revisit to our earlier lecture. So if you see, while we have discussed about the different temperature scale at that time, I have already told you that we are having some reference fluid. For example, in degree Celsius scale, we have taken the ice point and boiling point of the water as our reference points for defining the scale of temperature. Similarly, for Fahrenheit scale also we were having some reference points. Okay, so it means initially all our thermodynamic scales are nothing but depending upon some parameter and that particular some working medium, and based on the reference temperature of the working medium, actually we are defining our scale of temperature. Okay, but while we will be doing the thermodynamic analysis, it will be very much required to have some absolute thermodynamic temperature scale which is independent of the working medium. Okay, so what we want to have some absolute thermodynamic temperature scale which is independent of the working medium, so that we are actually able to easily analyze our system without considering the reference fluid. Okay, so if we try to see particularly our previous two slides, so our Carnot cycle provides basis for it. Okay, so Carnot cycle basically provides basis for defining the absolute temperature scale. How? Let me just explain. So what we are having in case of Carnot cycle, I have told you that if we are operating between the same temperature limits, irrespective of the working medium we are using in our different cycles, irrespective of the mechanical arrangement we are using, we will be having always same efficiency. Okay, so it means that we are having some specific behavior of these temperatures because of which we are always getting nothing but same amount of efficiency. So because of this, what will be happening, by considering the basis of Carnot cycle, we can define some absolute temperature scale. So for defining that, let me consider that I have some high temperature reservoir TH and some low temperature reservoir, say, or let me write, I have this first temperature as nothing but T1 and last temperature as T3, and I am having one heat engine A, which is operating, which is taking Q1 amount of heat. Okay. And this is my heat engine, reversible heat engine 1, and it is rejecting some Q2 amount of heat, say at temperature T2. And whatever the amount of heat it is rejecting, same amount of heat we are passing to some another reversible heat engine 2, and now it is rejecting Q3 amount of heat below. Okay. So from this first heat engine, let me write that we are getting W1 amount of work, and from the second heat engine, we are getting W2 amount of work. Now, in order to combine replace these two heat engines, I have taken some third heat engine, reversible heat engine 3, which is simply taking Q1 amount of heat from the high temperature reservoir, and it is rejecting Q3 amount of heat to the low temperature reservoir, and say it is doing some W3 amount of work. Okay. So obviously, if I write the formulation of efficiency for these three different reservoirs, reversible heat engines, so I'll be finding efficiency of first is nothing but equal to 1 minus Q2 divided by Q1. Efficiency of second will be 1 minus Q3 divided by Q2. And if I write the efficiency of third, which will be actually combined efficiency, so for the third system, efficiency will be nothing but equal to 1 minus Q3 divided by Q1. Now, one very important point I would like to highlight over here. We have already seen from the our thermodynamics that whatever the efficiency we will be getting for these two cycles, whatever the combined efficiency we will be getting, that should be equal to my efficiency eta 3. Okay, so that is what we have seen from our second proposition of the Carnot cycle. If we are operating between the same temperature limits, then obviously efficiency should remain constant. Okay, so it means I can simply say from the Carnot proposition, my efficiency is nothing but simply the function of high temperature and function of low temperature. Okay, so that is one very, very important point which we are able to see from our Carnot cycle, that efficiency is becoming only the function of temperature limits, TH and TL. Okay, so it means I can say in this efficiency, now this first term is constant, so I can simply say that for the first cycle, while I am getting this Q2 by Q1, Q2 by Q1 is say function of T1 comma T2. Then similarly, I can say for second cycle, Q3 by Q2 is nothing but function of T2 comma T3. Similarly, I can say for the overall cycle, Q3 by Q1 is nothing but function of T1 comma T3. Okay. Now, one thing I can do, I can write that my Q1 by Q3 is nothing but equal to Q1 by Q2 into Q2 by Q3. Okay, so that is what I can write, that my Q1 by Q3 is becoming nothing but equal to Q1 by Q2 into Q2 by Q3. So it means I can say, so now here I have taken the reciprocal. So if reciprocals are function of T1 and T3, obviously this Q1 by Q3 will also function of T1 and T3. Okay. So now what I am saying that my Q1 by Q3 is nothing but equal to Q1 by Q2, which is a function of T1 comma T2 multiplied by Q2 by Q3. So Q2 by Q3 is nothing but a function of T2 comma T3. Now we already know from our Carnot cycle that this Q1 by Q3 ratio is nothing but a function of T1 comma T3. So it means whatever this functional form I have got over here, the overall product of this functional form has to be only sole function of T1 comma T3. Then only this left hand side and the Carnot proposition will be valid. Okay, so this product function, whatever I am taking, f of T1 comma T2 into f of T2 comma T3, this overall product function has to be only the sole function of T1 and T3. So somehow we have to eliminate this T2 from here. Okay, so this condition will be applicable only if I define my f of T1 comma T2 as some function psi of T1 divided by psi of T2, and f of T2 comma T3 as nothing but some function psi of T2 divided by psi T3. Okay, so if I do this replacement, my Q1 by Q3 will be becoming nothing but equal to function of, so what was Q1 by Q3? Function of T1 comma T2 into function of T2 multiplied by T3. So function of T1 comma T2 is psi T1 divided by psi T2, and function of T2 comma T3 is psi T2 divided by psi T3. Okay, so now over here this will be cancelling out, and finally we will be finding that psi of T1 divided by psi of T3. So psi of T1 by T3 is nothing but a function of only T1 comma T3. Okay, so that is what which we have seen over here. Now what will be happening? This psi of T1 and psi of T3 can have multiple functional forms which will be satisfying this ratio of Q1 by Q3 equal to the function. Okay, so we may have over here number of functions which satisfy this equation. So we may have number of functions which satisfy this equation. But it was the Lord Kelvin, so it was Lord Kelvin who for the first time, what he has done, he has taken this psi of T1 as nothing but equal to T1 temperature in Kelvin scale, and psi of T3 as nothing but equal to T3 temperature in Kelvin scale. Okay, so from there then we have got that Q1 by Q3 is equal to T1 in Kelvin scale divided by T3 in Kelvin scale. Okay, so it was the Lord Kelvin first who used the simplified form for this particular function. Nothing but he has substituted this entire function with constant value of the temperature, and this temperature he has taken in nothing but Kelvin scale. Okay, so this particular formulation has actually satisfied, this has satisfied the absolute formulation of temperature. Okay, so this particular Kelvin scale has satisfied the absolute formulation of temperature. So because of that, Kelvin scale of the temperature is also known as absolute thermodynamic temperature scale. Okay, so now I will stop at this point and we will have further discussion on the absolute thermodynamic temperature scale in our next lecture.